Hello, welcome back to the second course in physics. We are still dealing with the field of electrostatics. And in this lecture, we will be talking about the capacitance and the electric field energy. The contents of this lecture will include some introduction and the definition of the capacitance, the capacitance of a single conductor will be derived, and the parallel plate capacitor, the capacitance for a parallel plate capacitor also will be derived. We will address the units of the capacitance, and then we will see how the capacitors in parallel, connected in parallel, how they behave, and also capacitors when connected in series. And we will discuss the capacitance of a system of conductors, and then finally we will be talking about the electric field energy stored in the in space. And to begin with, we have to mention that the geometry and the shape and size of matter or aggregates of matter in space, the arrangement and shapes and so on, play an important role in the responses of these systems, in the electrical responses and in the electrical phenomena consequently. And there is a quantity that combines these factors that affect the electrical behavior, namely the geometrical factors and the material factors. And that quantity, that physical quantity that combines or that includes those effects is the so-called capacitance of the system. And the capacitance is related somehow to the energy stored in the electric field, as we will see in the course of this lecture. First, we address the concept of capacitance. What is capacitance as a concept? If we consider two spherical concentric conducting shells, for example, and we describe this parameter for this system, we can reach some sort of understanding for this concept. So let's assume that we have two spherical conductors, conducting shells, which are concentric, sharing the same centers. And the radius of the smaller inside one is A. The radius of the larger, the outside shell is B. And let's assume that point P is a point on the inner shell, and point P prime is on the outer shell. And let's assume that the inner shell is charged with a positive charge plus Q, and the negative charge minus Q is residing on the outer shell. And we are interested in evaluating the electric field or the potential in the space. And from that, we will be defining the concept of the capacitance. So R, small r, is the position of a point somewhere between the two conducting shells, between the two conducting surfaces of the two shells. Keeping these in mind, we use Gauss' law to evaluate the electric field at any point in space, because we have a spherical symmetry for the problem. The charge distribution is spherical on both spherical shells. So it's easy to use Gauss law for the evaluation of the electric field, from which we can calculate the electric potential, as we have seen previously from the relation between the electric potential and electric field. So the electric field at point P prime outside on the outer shell is simply 0, because when we construct a Gaussian surface that includes both shells, the total charge inside the Gaussian surface is 0, which indicates that the electric field outside the outer surface is 0. So V at any point actually on the outer shell is 0. That's the potential potential on the outer shell, and the electric field between the spheres, between the spherical shells, also using Gauss law. If we construct a spherical Gaussian surface with radius r, small r, between the shells, then the electric field is q over 4 pi epsilon naught r square, which is characteristic of the spherical symmetry. And the direction of the electric field is radially outward from the inner shell to the outer shell, because the inner shell is the positive one. So in the points in the region between A and B, between the radius A and the radius B, between the two shells, E is equal to q over 4 pi epsilon naught r square, and it is in the direction of the in the radial direction. So knowing the electric field in the space between the shells, we can evaluate the difference in the potential between the two surfaces, and the difference in the potential, as we imagine that we are moving a unit charge, positive charge, from the outer shell to the inner shell. So delta V is V of the final destination, which is V of the inner shell, minus V of the initial position, which is V of the outer shell. V of the outer shell, at the outer shell, we have said that it's 0 simply. So delta V, which is simply Vp, V of the inner shell, this is determined from the integral from P prime to P of minus E dot dl, where dl is the path, the element of path that is taken as we move from the outer shell to the inner shell. And this is simply, if we substitute, this is simply minus q over 4 pi epsilon naught, and integral from B to A, that's where we are moving from the outer shell to the inner shell, dr over r squared. Remember that E is radial and dl is also in the radial direction, and this is equal to q over 4 pi epsilon naught times 1 over A minus 1 over B. 1 over A is 1 over the radius of the inner shell, and 1 over B is the radius, 1 over the radius of the outer shell. So this is the potential difference between the outer shell and the inner shell. And notice that this relation gives the relation between the voltage difference between the two surfaces and the charge residing on the positive surface on the inner shell. And the constant of proportionality is simply a constant that includes geometrical factors like 1 over A and 1 over B. It depends on the geometry of the system. And it also includes material factors, which is included within the permittivity of free space epsilon naught. Of course, if we don't have empty space between, we will have, instead of epsilon naught, we will have something else. So it depends, this quantity depends on the geometrical factors and on the materials. So the quantity Q over delta V, this is the relation between the charge and the potential difference. This quantity, as we said, depends on the permittivity of free space, which is material dependent, the material in between the shells, between the surfaces, and also depends on the geometrical factor, which is AB over B minus A, 1 over A minus 1 over B inverted, that is AB over B minus A. And thus, from the previous result, Q over delta V is equal to 4 pi epsilon naught times AB over B minus A. As we noticed, this quantity depends only on the geometry of the system we are dealing with and on the material in between the two surfaces. Any system of two conducting bodies insulated from one another, like this example that we have encountered, is called a capacitor. Such a system is called a capacitor, and the capacitance is a physical quantity of the system of two conductors is thus defined as the charge on the positive surface divided by the difference in the potential between the two surfaces or between the two bodies. So this is an operational definition of the capacitance of a system of conducting bodies. And the capacitance, as we have seen, is a system property of the conductors. It is a system dependent quantity in the sense that it depends on the geometry of the field lines, because we are calculating delta V from E dot dl, the path taken as we move from one surface to the other. E dot dl will include the strength of the electric field, and also the angle between the electric field and the path taken, and the electric field, the direction of the electric field, as we noticed, as we have seen before, is tangential to the field lines. So the geometry and the shape of the field lines with respect to the path taken from one point to the other as we evaluate the potential difference affects this quantity. So it depends on the geometry of the field lines, and also it depends on the medium in between. As we have seen, it includes the permittivity of space in between the two shells. So it is a system dependent in the sense that it is independent on the strength of the electric field and the charge on the conductors. It simply depends on the geometry of the system and whatever material is in between the surfaces. Does not depend on how strong is the electric field between them, or how much charge would I put on one or the other of the conductors. And now let's as a special case, let's consider the capacitance of a single conductor. Can we consider a single conductor as a capacitor? Does it have a capacitance? The capacitance is defined from the potential difference between two surfaces of two equipotential surfaces, two bodies, each one is an equipotential surface. So can we have one single conductor that can be considered a capacitor? The answer is yes. If we assume that we have a conductor that is isolated from everything else in the world, then we can assume that that it is, if it is isolated, we can assume that there is a second surface or a second body that is at infinity. And the two bodies, this single body that we are talking about, with the surface at infinity, we can consider it as two surfaces, and we can calculate the potential difference between them, and this will define the capacitance of the system, which is the isolated system, which is the body of interest and some surface at infinity. In this case, let's assume the previous example of two concentric spheres. If we take the outer shell, if we take it as an infinite shell with radius infinity, so the surface of the outer shell is at infinity, and B is simply infinite, and thus, if B is infinity, C of the system is simply 4 pi epsilon naught A B over B minus A as B goes to infinity, which is simply 4 pi epsilon naught A. So we notice that the capacitance of this system is simply dependent on the geometry of the body of the object, which is of radius A, spherical body of radius A in this example, and the medium between this, the surface of this body and infinity, which is epsilon naught, determined by epsilon naught here in this example. So this can be considered as the capacitance of the body of the spherical shell of radius A, 4 pi epsilon naught A. A is the radius. Now let's consider the parallel plate capacitor and the capacitance of the parallel plate capacitor. Capacitors, of course, can be of any shape, but if we have two plates of dimension that is large with respect to the spacing between them, to the distance between them, d, in order to have the field lines being perpendicular to the two plates and uniform, and we ignore fringing near the edges. If the plates are infinitely large with respect to the d, to the distance d, then we can simply neglect the fringing at the edges. And if we assume that one of the plates is at potential V and the second plate is grounded at potential 0, it's easy as a reference potential. We can calculate the potential difference between the two. And the potential difference between the two, since the electric field is constant, is simply related to the electric field. Electric field is E naught in between, is considered to be E naught. Delta V over D is equal to E naught, and this is like the example that we have derived from before between the potential difference between two plates and the electric field in between. And if we use Gauss' law to determine the electric field between the two plates, we can take a closed Gaussian surface of any shape, but we can take it of cylindrical shape for simplicity. And we notice that the electric field also only exists on one side of that cylinder. Then we have simply E times A, which is the total flux through the area of the Gaussian surface, is equal to Q, which is simply sigma A over epsilon naught. A is eliminated from both sides, and we have E naught is equal to sigma over epsilon naught, as this equation says. And this is simply Q over A epsilon naught if we replace Q over A for sigma. Accordingly, from the definition of the capacitance, which is Q over delta V, this gives the result that the capacitance of parallel plate capacitor two plates is equal simply to epsilon naught A over D, where we assume that empty space prevails between the two plates. So this is a general result for the capacitance of the parallel plate capacitor. Epsilon naught A, which is the area of the plate, of one plate, divided by D, the distance of the two plates. And now the units of the capacitance, the unit of the capacitance is called farad. And farad, from the definition of the capacitance, is simply the units of charge divided by units of voltage. And it is 1 farad is equal to 1 coulomb per volt, or 1 coulomb square per joule, if we use the definition of the potential in terms of energy and charge. This farad, this unit, is so large practically. So commonly in everyday life, we see other units are used, which are fractions of this huge quantity. Specifically, the microfarad, 1 mu f, microfarad, mu f, is equal to 10 to the minus 6 farad, 1 millionth of a farad. The picofarad is another commonly used quantity, which is 10 to the minus 12 farad. And these are practical quantities of practical use. Now, since we have defined the capacitance, we move to see how, if we connect capacitors in series or in parallel, what do we get? How do such an arrangement of capacitors, how does it behave in an electrical circuit? So for capacitors connected in parallel, for one thing, in the beginning, we define how do we draw a capacitor in the electric circuit. We draw it as a pair of parallel plates. So this parallel plates, this indicates a capacitor. So we have capacitor C1 with capacitance C1, another capacitor with capacitance C2, C3, and so on to Cn. We have n capacitors with different capacitances. And if we connect these capacitors such that one terminal of each one of them are the terminals of one terminal of each one of them is connected to the same point, to the same voltage, and the second terminal of each one of them is connected also to the same point, which is connected to the ground for simplicity here. This type of connection is called parallel. They are parallel. That means the voltage across each one capacitor is equal to the voltage across the second and the third and so on. The voltage is constant across any of the n capacitors. And we can view this connection as being an equivalent capacitor with capacitance C, this is the equivalent capacitance, as being connected between the point at voltage V and the ground. So we are interested in calculating the equivalent capacitance C of the equivalent capacitor for this connection in parallel. And in order to do that, we recall that the equivalent capacitor carries a total charge that is equal to the summation of the charges on the individual capacitors. So Q is equal to Q1 plus Q2 plus Q3 and so on to Qn. And we substitute for the charge Q in terms of the capacitance of each capacitor and the voltage drop across that capacitor. We notice that the capacitor drop across each capacitor is the same. That is characteristic of parallel connection. So the total charge Q is simply equal C1 plus C2 plus C3 plus times V, where Ci times V is the Qi, is the charge on any capacitor. And the equivalent capacitance, accordingly, C, is derived from the fact that C is equal to the total charge Q over V, which is simply C1 plus C2 plus C3 plus plus, which is summation of Ci. So for connection in parallel, for a set of capacitors connected in parallel, the equivalent capacitance is equal to the summation of the individual capacitors. And now we take capacitors in series. In the case of capacitors in series, the capacitors are connected this way, where one terminal of the first capacitor is connected to the point at voltage V, and then the second terminal of the first capacitor is connected to the terminal of the second capacitor, and the second terminal of the second capacitor is connected to the terminal of the third capacitor, and so on, until by the end, the second terminal of the last capacitor is connected to the ground. This is a series connection. And in this series connection, we notice that the charge on each capacitor is exactly the same, positive, negative, positive, negative. The charge on each capacitor is the same, but the voltage across the whole set of capacitors is equal to the voltage across the first one plus the voltage across the second plus the voltage across the third, and so on. So we can view this connection as being an equivalent capacitor connected between 2 points, the first point at potential V and the second point at potential 0, which is grounded. And in this case, in this type of connection, the charge is the same on each capacitor, as we mentioned, and the potential is the summation of the potentials. We substitute for V1 and V2 and V3 in terms of the charge, because the charge is constant, and the capacitance of each capacitor. So the total voltage is simply Q over C1 plus Q over C2 plus Q over Cn. That is the total voltage. And thus, if we divide all through by Q, then V over Q is simply 1 over C. V over Q, the total voltage divided by the total charge, is simply the total capacitance, or the equivalent capacitance. So the equivalent capacitance, V over Q, which is 1 over C, is equal to 1 over C1 plus 1 over C2, and so on. So for connection in series, the equivalent capacitance is determined by 1 over the equivalent capacitance is equal to the summation of 1 over C of the individual capacitors. 1 over Ci summation over all the capacitors. And if we have now a system of conductors in general placed in space of arbitrary shapes and positions, now we move to a more abstract argument, and we consider that the net charge on the system is 0. If we consider the net charge of the system is 0, and the system is isolated such that we cannot add charge or subtract charge from it, and each conductor is, we remember or recall that each conductor is an equipotential surface that is insulated from other conductors. So taking these into consideration, we consider a conducting body P that is placed over a conducting surface that is grounded, S. So the surface S is at potential 0, and the body P is at potential V sub P. Now, in this case, the capacitance is simply the charge on the body Q divided by the potential difference, V at the body minus V at the surface, which is simply V of the body. So Q over V is the capacitance of this system of the body and the surface. And now, if we
if we bring another body, P prime, that is charged with a negative charge, and put it in the region around near the first body, then we realize that the work required for moving a point charge, for example, from the surface S to the surface of the first body P, this work is decreased because of the presence of the negative body in the region. This body distorts the field lines in a way that the potential decreases. And if the work decreases and the potential decreases, then the capacitance increases, because the capacitance for the system is, if we don't change the charge, but the potential drops down, then the capacitance decreases. And we conclude that if we put a third body in the region, then it will affect the capacitance of the system. So the existence of objects nearby each other and interacting affects the capacitance of the system. And now we consider that a simple case where we have a parallel plate capacitor, and we assume that the field lines starting from the positive plate all end in the negative plate. So we don't have any stray field lines as an assumption. If that's the case, then the total flux phi, which is related to the number of field lines, of course, is equal to the total charge on the positive plate divided by epsilon naught. That is, if all the field lines are enclosed, they start from one plate and end on the other plate. And thus, the capacitance is simply Q over delta V is simply epsilon naught phi divided by delta V. And notice here that there is a relation between the difference in potential between the two surfaces and between the flux or the number of lines that originate from one surface and end on the other surface. There is this connection between the potential difference between the two surfaces and the flux lines or the field lines in between. And the proportionality constant is a constant that is related to the geometry of the system and the material in between. So if we consider a general case of several bodies, consider three bodies, for example, here, and we consider these bodies are charged and they are interacting. Some of them are positive, some of them are negative. And we draw the field lines. And in order to calculate the flux, we draw also surfaces, like surface between body 1 and body 2, a surface between body 2 and body 3 to calculate the flux between the different bodies. And we also construct surfaces in order to calculate the flux through the surfaces going from one body to infinity, the flux lines going to infinity. So in that case, if we assume that there is a Gaussian surface around one body, and we want to calculate the flux through this Gaussian surface, this flux is due to the field lines that go from this body to the second body, and to the third body, and to the fourth body, and to infinity. The flux lines going to infinity define a quantity, and the flux lines from one body to the other define other quantities, as we will see. So in this case, like for example, phi ij is equal to A sub ij times Vi minus Vj. We noticed from the previous discussion that there is a linear relation between the difference in potential between two bodies and the flux lines between these two bodies. So if we set this proportionality or this relation, linear relation, as phi between the two bodies I and j, number I and number j, is proportional to the potential difference Vi minus Vj, and the proportionality constant is called Aij. So in this case, like for example, phi ij is equal to minus phi ji, because the field lines, if they are originating from I and ending in j, then the direction is opposite to as if we move from j to I. So the flux is phi ij is equal to minus phi ji. And Aij is equal to Aj from the previous relation, as defined by this relation. If we set phi ij is equal to minus phi ji, that means Aij is equal to Aj, and this is a positive quantity. So with this definition, we also define the phi ii is correlated with the field lines originating from a body I and ending in infinity, going to infinity. So it's Aii times Vi. Vi is the potential of the body itself, and where the second body of interaction is at infinity, of course, and its potential is 0, as we have discussed before. So with these concepts in mind, we have, if we construct now a Gaussian surface around the first body, Q1, the charge enclosed in this Gaussian surface around the first body, Q1 is equal to epsilon naught times the total flux lines across the surface, which is phi from this first body going to infinity, the field lines that are going to infinity, plus the field lines that are due to the interaction of the first body with the second, plus the flux which is due to the field lines originating from the interaction of the first body with the third. And this is simply equals to epsilon naught times A11 times plus A12 plus A13 times V1 minus A12 V2 minus A13 V3 from the definitions. So this is the relation between Q and the flux lines. And then here we define the capacitance, the self-capacitance. For the first conductor, for example, is C11 is equal to epsilon naught A11 plus A12 plus A13, which is coming from the different contributions due to the flux lines coming from the different interactions. And the mutual capacitances are coming from the interactions between the different bodies. So C12 is equal to minus epsilon naught A12, which is equal to C21, and C13 is equal to minus epsilon naught A13, which is equal to C31. And this is coming all from the definition and from the relation that we have derived a little while ago. And now we can rewrite these quantities as Q1 is equal to C11 times V1 plus C12 times V2 plus C13 times V3. And similarly, we can derive the charges on the second body and on the third body with the relation with these parameters, the capacitance parameters. Q2 is equal to C21 V1 plus C22 V2 plus C23 V3. And Q3 is equal to C31 V1, C32 V2 plus C33 V3. And notice the symmetry of these relations. So now this with this construction, this gives the capacitances. Cij is equal to Cji, which is equal to minus epsilon naught Aij for I does not equal to j. So if the body is interacting with another body, and if I is equal to j, then we have the self-capacitance, which is Cii or Cij, Cjj, whatever it is equal to epsilon naught times the summation from k is equal to 1 to 3. In this case, we have three bodies, Aik, and we sum over the interaction of the first body with the three bodies. So this defines the capacitance of the system, and this can be generalized to n conductors. And now let's talk about the electric field energy in space. Now the work done to charge a capacitor, in order to charge a capacitor we need work. The work done to charge the capacitor is stored as electrostatic potential energy in the system. And the work is simply determined by the integral. We start charging the positive body with a positive charge, and of course the negative body, the second body, with a negative charge. So we assume that we start from zero charge, zero potential. At a certain point, the potential on the body is V prime, and we add charge dq prime at a time, and then we integrate from the initial charge on the body, which is 0, until we reach the final charge on the body, which is q. And we do this integration, v dq, that is the work done to add the charge dq, and we integrate. And this, in order to do that, we replace v prime by q prime over c. And doing the integration, this gives us q square over 2c. So thus, this work done is stored in terms of electrostatic energy, and the electrostatic energy is simply q squared over 2c, which is 1/2 cv squared. We just substitute the different quantities, which is equal to 1/2 qv. So this is the electrostatic energy stored as a consequence of the charging of the capacitors. For a parallel plate capacitor, for example, which is a simple system, we have U is equal to 1/2 CV squared, because it's a general relation. And we substitute for C for the parallel plate capacitor epsilon naught A over D. So we have epsilon naught A V squared over 2D. And we substitute for the value of V, the potential difference, in terms of E times D, the distance between the two plates. So we arrive at the formula U is equal to 1/2, that's the total U, 1/2 epsilon naught E squared A times D. And remember that A times D is the volume within the capacitor. So the density of the electrostatic energy is simply 1/2 epsilon naught E squared. And this relation is applicable everywhere in empty space and free of charge space. The total electrostatic energy is obtained by, in a certain region of space, is obtained by integrating the density of the electrostatic energy. So in order to obtain in a general form, U is equal to 1/2 times the integral of E squared times d tau, and this gives us the total energy stored within a volume in space if we integrate over that volume of space. At this point, I would like to conclude my lecture, and thank you for listening.